A quantum computer is a real or theoretical computer that exploits quantum phenomena like superposition and entanglement in an essential way. It is widely believed that a quantum computer could perform some calculations exponentially faster than any classical computer. For example, a large-scale quantum computer could break some widely used encryption schemes and aid physicists in performing physical simulations. However, current hardware implementations of quantum computation are largely experimental and only suitable for specialized tasks. The basic unit of information in quantum computing, the qubit, serves the same function as the bit in ordinary or classical computing. However, unlike a classical bit, which can be in one of two states, a qubit can exist in a linear combination of two states known as a quantum superposition. The result of measuring a qubit is one of the two states given by a probabilistic rule. If a quantum computer manipulates the qubit in a particular way, wave interference effects amplify the probability of the desired measurement result. The design of quantum algorithms involves creating procedures that allow a quantum computer to perform this amplification. Quantum computers are not yet practical for real-world applications. Physically engineering high-quality qubits has proven to be challenging. If a physical qubit is not sufficiently isolated from its environment, it suffers from quantum decoherence, introducing noise into calculations. National governments have invested heavily in experimental research aimed at developing scalable qubits with longer coherence times and lower error rates. Example implementations include superconductors and ion traps. Researchers have claimed, and are widely believed to be correct, that certain quantum devices can outperform classical computers on narrowly defined tasks, a milestone referred to as quantum advantage or quantum supremacy. These tasks are not necessarily useful for real-world applications. As a result, current demonstrations are best understood as scientific milestones rather than evidence of broad, near-term deployment. In December 2024, Google's Willow chip achieved below-threshold error correction, a milestone 30 years in the making, while global government investment in quantum computing reached $10 billion by April 2025. For many years, the fields of quantum mechanics and computer science formed distinct academic communities. Modern quantum theory was developed in the 1920s to explain perplexing physical phenomena observed at atomic scales, and digital computers emerged in the following decades to replace human computers for tedious calculations. Both disciplines had practical applications during World War II. Computers played a major role in wartime cryptography, and quantum physics was essential for nuclear physics used in the Manhattan Project. As physicists applied quantum mechanical models to computational problems and swapped digital bits for qubits, the fields of quantum mechanics and computer science began to converge. In 1980, Paul Benioff introduced the quantum Turing machine, which uses quantum theory to describe a simplified computer. When digital computers became faster, physicists faced an exponential increase in overhead when simulating quantum dynamics, prompting Yuri Manin and Richard Feynman to independently suggest that hardware based on quantum phenomena might be more efficient for computer simulation. In a 1984 paper, Charles Bennett and Gilles Brassard applied quantum theory to cryptography protocols and demonstrated that quantum key distribution could enhance information security. Quantum algorithms then emerged for solving oracle problems, such as Deutsch's algorithm in 1985. the Bernstein-Vazirani algorithm in 1993, and Simon's algorithm in 1994. These algorithms did not solve practical problems, but demonstrated mathematically that one could obtain more information by querying a black box with a quantum state in superposition, sometimes referred to as quantum parallelism. Peter Shor built on these results with his 1994 algorithm for breaking the widely used RSA and Diffie-Hellman encryption protocols, which drew significant attention to the field of quantum computing. In 1996, Grover's algorithm established a quantum speedup for the widely applicable unstructured search problem. The same year, Seth Lloyd proved that quantum computers could simulate quantum systems without the exponential overhead present in classical simulations, validating Feynman's 1982 conjecture. Over the years, experimentalists have constructed small-scale quantum computers using trapped ions in superconductors. In 1998, a 2-qubit quantum computer demonstrated the feasibility of the technology, and subsequent experiments have increased the number of qubits and reduced error rates. In 2019, Google AI and NASA announced that they had achieved quantum supremacy with a 54-qubit machine, performing a computation that classical supercomputers would take an estimated 10,000 years to complete, a claim subsequently disputed by IBM, which argued the calculation could be done in approximately 2.5 days on its Summit supercomputer, with optimized algorithms, sparking a debate over the precise threshold for this milestone. Recent milestones in quantum computing have increasingly focused on controlling decoherence through quantum error correction. In 2024, researchers demonstrated theoretical and practical approaches for high-threshold, low-overhead fault-tolerant quantum memory. These developments represent a critical step toward scaling systems beyond the noisy, intermediate-scale quantum era into reliable, fault-tolerant computing architectures, though large-scale physical implementation remains an ongoing engineering challenge. Computer engineers typically describe a modern computer's operation in terms of classical electrodynamics. In these classical computers, some components may rely on quantum behavior, however, because they are not isolated from their environment. Any quantum information eventually quickly decoheres. While programmers may depend on probability theory when designing a randomized algorithm, quantum mechanical notions such as superposition and wave interference are largely irrelevant in program analysis. The classical in classical computation thus refers to the computational model, not to whether the microscopic physics of the hardware is ultimately quantum mechanical. A conventional digital computer can be described by classical states and transition rules. Memory stores bits, while logic elements transform one configuration of bits into another. This computational behavior is not tied to electronics, and can be abstracted through the idea of a Turing machine, a mechanical device that performs deterministic transformations on a finite state. In principle, the same classical transition rules can be implemented by some entirely classical mechanical device, possibly with a fixed slowdown in physical time. If a classical computation uses randomness, this can be modeled as access to random classical bits rather than as coherent quantum information. A quantum computer, by contrast, uses coherent quantum states, so that superposition, relative phase, and interference are part of the computation itself, and has no classical counterpart. Quantum programs instead rely on precise control of coherent quantum systems. Physicists describe these systems mathematically using linear algebra. Complex numbers model probability amplitudes. Vectors model quantum states. And matrices model the operations that can be performed on these states. Programming a quantum computer is then a matter of